This is a series of free tutorials recorded in the framework of the European GNU Radio Day Conference 2024, aimed at new users of GNU Radio and its graphical interface GNU Radio Companion. In the first tutorial, we will discuss how to get familiar with GNU Radio Companion, what kinds of data are streamed and processed, and assess some of the learning capabilities of GNU Radio on synthetic data, including such awkward features such as imaginary voltage and negative frequency. On the second tutorial, we'll see how to process the samples, radio frequency samples collected or synthesized in this case, and how to write a custom Python processing block. And finally, on the third tutorial, we'll see how to make GNU Radio and GNU Radio Companion interact with external tools. So if we launch GNU Radio Companion, for example, with command GNU Radio Companion, then we will have an empty screen with a blank canvas for working. All the libraries, all the processing blocks of GNU Radio are visible here on the right. Now we don't want to go searching for all the possible capabilities of GNU Radio, so using the magnifying glass we can search for keywords. In GNU Radio, all data are generated with sources will be processed until they reach a sink. So for example, if we consider the signal source, which is a signal generator, we see by double-clicking on the block that we have an ID, we have a type, and we have various properties. Now, throughout this tutorial, I will be using some of the viewing properties. So first of all, I'll be showing all block IDs, which you might have disabled by default. So block IDs allow you to know what is the name of each class that is instantiated by GNU Radio Companion, and will show the parameter expression so that, for example, you see here that the value 32k is coming from the fact that we associate semprate with this variable. Now you see here that the output of this block is a blue rectangle. What is a blue rectangle? If we go in help and types, you see here that blue rectangles are complex floating point 32, so single precision floating point with a real part, imaginary part. The other type that we're going to use is the float 32, which is a single precision floating point number, only a real part, no imaginary part, which will be orange. So if, for example, we double click on the block and change complex to float, we see now that the output is orange. We wish at first to have the most common sinks, which are time domain and frequency domain. So the time domain sink is a time sink, and if we go here a bit below, GNU Radio is using the Qt graphical interface. So if we go into the Qt graphical interface time sink, here we're going to have this display with 1724 samples, and we see that as we are generating 32 kilosample per second, we are here syncing 32 kilosample per second. Of course, if you connect these two blocks together, they will not fit because we have real parts feeding imaginary input, so we need to double click and change the type to float. And now the arrow has become black. If we were to execute this flowchart, GNU Radio would warn us that there is no timing feature because this is a virtual source, this is a virtual sink, and GNU Radio does not know what a second is when streaming 32 kilosamples per second. So when we have only virtual blocks, and only if we have virtual blocks only, no real hardware, we need to slow down. And like in a car, we need to have a throttle pedal that slows down, that tells GNU Radio what 1 second is. So the source here will generate 32,000 samples. The throttle block will say wait until a second has elapsed, and then it will ask for new data. Again, we switch to float. And if we run this, by default, the ID of the block is default, which is not allowed, so that when we run, GNU Radio will ask us to save the file. Now, this file should be a Python compatible expression, so it cannot start with a number, it cannot have a number at the beginning, so just give a name here that is Python variable compatible. And you see here that we have our very first output, which is the time domain display. Similarly, we can have a frequency domain display with a spectrum analyzer, which again has to be switched to a floating point, real part only. And if we run this, we have, in addition to having the time domain, we have a frequency domain. We see here the two peaks associated with the fact that the real cosine, as we were generating here, is exponential of j omega t plus exponential of minus j omega t. So we have minus omega and plus omega, the two peaks. Because the spectrum of a real function is an even spectrum, we can actually ask to only have half of the spectrum, since there is redundancy between the negative part and the positive part, and now we have only one positive peak at 1 kilohertz as requested in this part. At the moment, we have not done anything much more than signal processing with NumPy or Octave, because it's a static simulation. So now what we can try to do is to change a frequency content here. Instead of having a fixed value, we can give it a name, let's say frec. Now when you create a variable, this is a Python that says equal frec, and of course we have not defined the variable frec, so that GNU Radio is unhappy. To create a variable, which is a Python expression, we're going to create a variable as done here, and we call it, the ID of the variable is the name, so this would be the Python expression frec equals 0, and let's make it equal to 440. Now GNU Radio is happy because we created a frec variable over here, we're using it over here, and when we run the flowchart, we have our 440 Hertz sine wave. Now this is not very dynamic still, because this variable is fixed. So rather than having a fixed variable, we can create a slider, which is in the GNU Radio naming convention called a range. And if we have a range now, we can actually create the variable frec. The variable frec can go from 0 Hz DC, to a maximum value meeting Shannon sampling frequency, which is sample rate over 2. Notice that we will not write 16,000, but sample rate over 2. Python expression that says sampling rate divided by 2, so that in case we change the sampling rate, the change will be propagated to all the other blocks. Now there is a conflict because we have two definitions of frec, one static, one dynamic. You can click on the block and comment so that there is no conflict between these two definitions. And if we now run this flowchart, you see here that we have a slider, and this slider allows us to dynamically change the properties of the simulation. This is one of the big highlights of GNU Radio, to make quick and dirty signal processing flowcharts, and then to try each and every step of the simulation. Very often when we're going to run a signal processing chain, we are going to have excess information, since as we are advancing in the demodulation process, we are removing information as we are going further, and the less information we have from Shannon information theory, we know that the narrower the spectrum. Now a narrower spectrum, since a spectrum is going from minus Nyquist frequency to plus sampling frequency, narrowing a spectrum means decimating or keeping 1 in D samples. So one way of simulating the fact that we decimate is to say we keep 1 in D samples over here, and because the data stream will be decimated, we need to remember the decimation factor. GNU Radio will not know this for you. GNU Radio requires that you remember what is your data stream. If we keep only 1 in D sample at this block, then we start with sample rate, but here we end up having sample rate over D. Because this D variable will be used multiple times in the flow graph, like in any programming language, when you have multiple uses of the same variable, we wish to create a variable rather than duplicating the quantity. So here we create a variable D, which allocate to a variable value of 3 to keep 1 in 3 samples, and this is the D quantity that we're using here. Because all our flowchart uses real numbers, we switch to a real quantity, and we end up connecting all the blocks. Because we only keep 1 in D sample, we must make sure to decimate also the data rate on the sinks, so that the sampling rate is consistent with the new value. And when we run this flowchart, indeed we see that rather than having an upper frequency of 16 kilohertz, which is half the sampling rate, initial sampling rate of 32 kilosample per second, now it's 1/3 of this value. And as we are sweeping the frequency on the input, we have sample rate sample per second, we're allowed to reach the Nyquist frequency. And what happens when we reach the Nyquist frequency, you see that the signal returns back to baseband being defined as the spectral part that is centered on 0 and going up to the Nyquist frequency. So here we are slowly going up to the Nyquist frequency, and when we reach the Nyquist frequency, the signal is aliased back to baseband, and we see that we are left and we return back to baseband. Now we might think that the signal is bouncing back into the baseband, and that's not exactly what is happening. Let's see with an imaginary quantity what is actually real happening. So if we now change all our real quantities with complex numbers, so actually we just switch all the blocks back to the complex default behavior, now we see that the spectrum is now a full spectrum because there is no reason for the spectrum to be even once we've reached complex quantities. And this time the range is no longer going from 0 to separate over 2, but a frequency can be a negative quantity as well. What is this awkward variable that is an imaginary voltage and a negative frequency? So to get a bit of an insight into this awkward value, we run the simulation. Now we see here that the frequency can be positive and it can be negative. What is the difference between a negative and a positive frequency? If you look closely here, I have a positive frequency and I'm going to switch on the trigger, middle button of the mouse, and trigger mode auto will allow me to stop the sine wave from sweeping the oscilloscope screen, and you see that when the frequency is positive, the imaginary part, which is the red part over here, is before the blue part, the real part. If on the hand I switch to a negative frequency, you see that now the imaginary part is after the real part. So the imaginary voltage, of course, does not exist. We only have real part and imaginary part because we've created an IQ demodulator with I and Q, two quadrature local oscillators, cosine of omega local oscillator t and sine omega local oscillator t. And these two voltages are probed. These can be probed by an oscilloscope. They are real voltages, but they happen to match the imaginary algebra where the cosine and sine are in quadrature. So we have something which is a cos plus j a sine, which match the algebra of complex quantity. And we see that a negative frequency is something when the imaginary part is later than the real part, and a positive frequency is two voltages where the imaginary quadrature component is before the real part. So this allows you to see a little bit what are the meaning of this awkward quantity, and furthermore you can have a new insight into what aliasing means if we bring now this complex number. Remember when we had a real part, a real output cosine, we had two peaks, one at minus omega and one at plus omega, and we had the feeling that when we reach the Nyquist frequency, the peak here would bounce back into the baseband. When you have a discrete time Fourier transform, usually people say that the spectrum is periodic. Why do we say spectra are periodic? Because actually when you reach the Nyquist frequency, you see that it's not bouncing back, but it's coming back into the negative frequency range. So when we have a spectral component reaching minus the Nyquist frequency, it comes back into the plus Nyquist frequency, and similarly like this. So this means that actually whatever is happening here on the right hand side of the spectrum will be reflected into the negative part of the spectrum over here, hence this definition of periodic spectra. So this also tells you that whenever we decimate, we must make sure that we low pass filter to make sure that we do not alias signal back into the baseband. Now in order to low pass filter, we're going to shift a little bit these signal processing blocks over here and insert a low pass filter. So the low pass filter here is this block, and so we've seen that the other block is just the taps, so the coefficients of the filter. Here we have a full low pass filter, and we need two quantities, the cutoff frequency and the transition width. Now the cutoff frequency is quite obvious. This is the frequency at which the spectral components start being removed by the low pass filter. So in our case, we start before decimating with sempre rate sample per second, and we've seen that after decimation the spectra will go from minus sempre rate divided by 2 divided by d up to plus sempre rate divided by 2 divided by d. So this will be our cutoff frequency, sempre rate divided by 2 divided by d. Now the transition width is slightly more tricky. This will actually tell us how quickly, how sharply the filter must decay. Ideally, we might want to say we want an infinitely narrow filter, so we just want a transition width of 0 Hz. Well, if we were to execute this flowchart, GNU Radio will tell us that the transition width must be positive. Of course, a filter must slowly decay. How slowly? Consider this. If I was to write here a transition width of df, it means that the Fourier transform must be detailed enough to be able to say what is the weight at a frequency f and another weight at frequency f plus df. What is the frequency resolution of a Fourier transform? When sampling at sempre rate and taking a Fourier transform over n samples, then the spectral resolution is sempre rate divided by n, because the Fourier transform of a signal over n samples spans from minus half a sampling frequency to plus half a sampling frequency, so a span of sampling frequency divided by the n samples. So the spectral resolution of the Fourier transform is sempre rate over n. Now consider that if we were to define the transition width of df, we must select n large enough that sempre rate over n is smaller than df. Or in other words, this means that n must be bigger than sempre rate over df. This is the frequency resolution of the Fourier transform in the frequency domain. Now, another way of saying that the convolution theorem transposes time domain and frequency domain weighted filtering is to consider that a filter that outputs samples n is a weighted sum of taps b multiplied by the weighted pass quantities x n minus k. And this sum goes from 0 to n minus 1, the n samples that we are considering here. And these two n in the frequency domain, in the time domain, are the same n because a Fourier transform is bijective. There is as many samples in the time domain as there are in frequency domain. So you see here that when calculating one output, we must make a weighted sum of n terms, and this n here is determined by the transition width df. So we must make sure that n remains reasonable if we want to not overload the computation capability of our computer. So another way of saying this expression is to select df so that it's equal to sempre rate divided by n, with n the number of taps. And we know that something like n in the order of 64 to 68 will be something that is reasonable. So here what we can do is select df, the transition width, as sempre rate over 128. Now you see what I've just done. I've been writing comments in the advanced tab, and this is very useful when you want to remember your line of thought or the reason for writing something. So always put comments in your flowchart to remember how you thought of defining some of the parameters. So you see here we have a cutoff frequency of 5 kHz, which matches half the output frequency here once we've decimated, and we've generated a transition width of 250 Hz. If this 250 Hz is too slow, probably your problem has been misstated and you should cascade low-pass filters rather than trying to make one filter with a very sharp transition. Now see here in the baseband we have a signal with relative power of -8 dB, and if we move beyond the Nyquist frequency, well, because there is no noise, we still see a bit of leftover, but now it's -78, 79 dB. So the signal dropped by 70 dB between, and the time domain is hardly visible here, between baseband and the second Nyquist zone. So we've effectively removed aliasing effect because by low-pass filtering we've removed all the unwanted spectral characteristics. Now, filtering and decimating are such common operations that usually you do not low-pass filter before decimating, but you actually decimate inside the filter. So be aware that here this decimation will take place after the low-pass filtering, after the weighted sum. Of course, if we were to do it before, then we would alias and there would be no way of removing this unwanted spectral component. Again, we comment out this block because it's no longer used, and we take the output of a filter to feed the time domain and frequency domain displays. And as before, we now have efficient filtering, minus 8 dB when we are within the baseband, and minus 79, minus 80 dB when we are in the second Nyquist zone. So we see that the low-pass filter has efficiently filtered out the unwanted spectral component. So now, as a conclusion to this presentation, we might want to interact a little bit with these flowcharts. And if we quickly look at what was the output, whenever we're executing GNU Radio Companion, you see that we output a Python script, and this Python script can be edited. So for example, if we look here in our Python script, it starts with all the initialization of the queued graphical interface, but what we're interested in is the low-pass filter. So the low-pass filter here has been defined as a low-pass filter with the sample rate, the sampling frequency, and so on. And here we can interact with this flowchart and consider that we can, for example, print the length, if we want to know the number of taps, of this filter here. We can ask the method taps, which provides the taps of the vector taps, and we display the length. Now we can execute this edited example here, and when executing, we see that there is a display of the taps. If now we reduce the number of we reduce the transition width, say, tenfold. So we want, from our previous theory, we are going to generate 10 times more taps. Indeed, if we execute now this example, we see that we have no 309 coefficients, but we have 3000 coefficients. So indeed, dividing by 10 the transition width will multiply by 10 the number of taps. However, if I regenerate the Python script here, you see that all the changes we just made were lost because we've regenerated the Python script. So the print of length of taps has been lost. What we can do is actually use a Python snippet as the means of generating a piece of code within the generated Python. So the Python snippet can be located in the main after the initialization, after the start, after stop, or before the blocks. And here we can print the length of what we just did before. So we saw that the low-pass filter is called low-pass filter 0, and we've just seen that we have a taps method that generates the length of coefficients here. And now if I execute this flowchart, we can see here the 309 displayed as before. And if I change to 1280, the transition width as just before, we have 3000 samples, 3000 coefficients. But the beauty of this is that now the modification has been introduced within GNU Radio Companion and will not be lost during the next execution. Now be aware, and this will be the topic of the next tutorial, in this GNU Radio Companion we're generating variables, we're generating various processing blocks, such as the low-pass filter over here, the analog source, and the throttle block, and we're connecting them together. So we're just connecting C++ libraries or a library called to each other, but we do not have access at this stage to the IQ stream. What we're going to do in the next tutorial is to assess how to access the IQ coefficients.